Friends, today I'm going to discuss the Black-Scholes formula pricing by expectation. And at the time, they had no idea what the discounting rate should be, and they didn't realize whether the security itself, what kind of mu, or what they call the drift, it should have. Okay, so miraculously, the problem went away with dynamic hedging, but effectively, any option operator knows that it can go away via an operation called put call parity. So I'm going to discuss both today. So dynamic hedging is the argument of Black-Scholes. Again, Black-Scholes did not find an option formula. They just figured out that you can remove the drift of the underlying security via dynamic hedging. I'm going to use a tablet to make things simpler. So friends, let me now explain Ito's lemma, or the Ito integral to start with. So you have ST plus 1, this is, say an asset or anything indexed by time, T, ST plus 2, etc. It works by taking a function at ST and multiplying it by ST plus 1 minus ST. So if you see, you take a function here and you're multiplying by what happens after. It's called non-anticipating. In real life, you make a decision in the morning on what to buy, and your return is what you bought, the quantity you bought, times the variation in what you bought. So what happens after? It's called non-anticipating. Non-anticipating strategy, which is pretty much what happens in real life. So this is called the Ito integral, because if you take the sum, so it's going to sum f of si plus 1 minus si. Okay, so and you take it to the limit, you will always have that lag, what happens between the decision and the result, and that you cannot compress. So this is Ito. Now, needless to say that the Russians have their own version. And that second integral is called the Stratovich Integral, where it's sort of anticipating and sort of not. ST plus 1, f of some average, ST plus, say, ST plus 1 divided by 2, times ST plus 1 minus ST. And then as a summation, you have a function of, like the one we have above, now we're taking a sum. So it's sort of anticipating that if you take very small, if you take it at the limit to make it an integral and small limit, it risks becoming smooth. The one above, Ito, never becomes smooth. And then finally, we have the Jim Kramer Integral. And as follows: ST plus 1. You take f of ST plus 1, in other words, you know what's going to happen at the end of the period, the next period, times ST plus 1 minus ST. So you know the answer. So let's apply that to COVID. ST, you make a decision on what happens to COVID, to what's your risk based on information at times ST, and then see how many people are going to die based on that policy, how many are going to survive. So it's non-anticipating. But in perfect hindsight, we should have done that. So that's called the Jim Kramer Integral. And effectively, there is a Kramer, one of the pioneers of probability theory, came before Kolmogorov, before it was really formalized and put on strong mathematical grounds. And he had great ideas. We know from his classification of his probability distribution, he was an actuary. And actually, he welcomed the fact, he said, once I saw Kolmogorov's work, I realized that probability could be a science. Because now you can do rigorous work with it. Anyway, so there is a Kramer, a Swedish fellow who worked about 100 years ago, different from Jim Kramer, who goes on CNBC. So this introduces us now to the notion of stochastic differential equation based on the fact that in the first case, in the Ito case, it never becomes smooth. You always get jagged because you never really catch up with that interval delta t. Of course, when you narrow the interval, the variation is going to be, on average, smaller, but still, you still have that gap in periods. Thanks. Friends, we saw the concept behind Ito's lemma, but there's more. Now, let me try to prove the Black-Scholes, rederive the Black-Scholes equation, and at the same time give us more insights about derivative pricing and the limits of working with the limit. Start with the following stochastic differential equation. W stands for Wiener. So, and Ito's lemma allows us to derive a function of, say, s and time, okay? And the dynamics of that function. But there's one central thing about Ito's lemma. We have a multiplication table for infinitesimals. Anything dt is small enough that anything multiplied by dt will naturally be 0. dw by dt will be 0. But dw squared is going to be equal to dt. Why? No matter how thin your time slice will be, the function will always have a second derivative. So you always have, but you can compress it, and that would be equal to dt. So in other words, you cannot, and you have a race, so the ratio of dw squared over dt goes to 1 at the limit. And the derivation is via mean square limits. Don't be fooled by thinking that because the variance of this is upstairs, a Gaussian, therefore the variance of Gaussian over time for a process is going to be proportional, is going to be time. The sigma square equal delta t, so it's not the same here. So we take into the limit, and we're going to talk about infinitesimals, which, as we'll see, would be critical for deriving the Black-Scholes equation. So Ito's lemma now allows us, thanks to this multiplication table, to have df, a derivative of this function of s and t. First derivative with respect to time. First derivative with respect to s. Let's keep s as it is, not expand. Plus second derivative the s squared. Now, let me change color quickly. The s squared, we go above, we have a term in t, dt squared goes to 0. We have 1 dw dt equals 0, and we have sigma square s square dw square, which is going to be dt. So we replace this by s square sigma square dt. As you see, we only have one term, the first derivative, that depends on s so far, the random term. Now, what did Black-Scholes do? They constructed a portfolio pi, call, and then assume an arbitrary number minus delta s, delta proportion of shares, long or short. So, and let's see what happens, how we can derive the delta. Right, at infinitesimal variation, d pi is going to be what? Of course, as we saw above, df t time decay, plus, repeat what we have above, plus, of course, the second derivative, minus delta S. Now, set delta equal the infinitesimal hedge, hedge ratio, and guess what? We got rid of the terms in S. So we don't have any more random terms. And if you set the pi equals 0, you can construct basically by removing the set, you can construct a portfolio that has 0 variation. Allora, the return mu disappear from the equation. And yeah, of course, this is sigma square s square dt. So we end up with a final differential equation, which means theta equals gamma. And that's the genius of the Black-Scholes equation, is they created a mechanistic relationship between S and the call. I mean, call here is F. Actually, it could be generalized for any underlying. They created a mechanistic relationship. It's not stochastic. They remove the mu as a return. And of course, that only happens at the limit if you can take things in practice to the limit which you can't. There's a bigger problem, the DW, okay? We're talking about this apparatus based on a Gaussian. Now, dynamic hedging is the equation below, I mean instantaneously, but you can make it discrete. You can make theta equal gamma over a discrete period, but it's more complicated. And of course, under any probability distribution you want, which I tried to do, particularly recently with a paper showing how we can price using power laws. A power law return for ds. Have any distribution, but you have to be very careful about specifying the process. But the theta equal gamma is universal. That's my anti-fragile idea. You shall not have anti-fragility for free. You get enormously rich. And you should never sell convexity without being compensated for it. Fragility should earn your price. So all that is part of that that it's no longer a stochastic. It's PDE, or not stochastic on paper. PDE, we can solve it. Now, how do you solve this PDE? You set boundary condition, a maximum like f of s and t for a call, at expiration t, not small t, cap t, equal max s minus k 0. You can have different class of payoff. You can have a combined payoff. This with f, you can price anything. Same equation. Of course, you can have, and if you have difficulties getting the equation right, you put other boundary conditions. You put, at infinity, the call is going to be equal, converts to s, or the call divided by s, it converts to s minus k. Set k equals 0, the call is going to be s. F can be a put, same argument. Sorry for my mistake, we're using C, you could use F, any derivative off of that. That is, that has other subconditions, okay? Not all derivatives, it's more complicated when we start talking about Era tum, there is a typo here. It was ds, not s. So delta times ds, not s. Finally, note the following difference between standard calculus and stochastic calculus. That integral to the left of integrating x dxt, so if you were to discretize it, it would be xt times the difference, some difference xt and st minus delta t. It would be, of course, half of 0 x 0 would be 0 would be half of x squared t. Whereas in stochastic calculus, it's not, because the dxt doesn't quite overlap with xt. So you're going to have 1/2 of xt squared, cap t squared, minus